So now with this background, we are now ready to write the full algorithm for training RBMs using Gibbs sampling. So before that, we'll just do a quick recap of what was that quantity which was irritating us, and now whether we have been able to take care of that quantity, right? So what we were interested in, as usual, is the gradient of the loss function with respect to some parameter. The parameter was wij, and we did some trickery and we figured out that this is actually a sum of two expectations, right? And our problem was that we cannot compute this expectation because we cannot draw samples from this joint distribution. I've written it as P of V comma H, but it's the same as P of X in the previous discussion. But now with this Gibbs sampling procedure, I have given you a way of sampling from this distribution, or in other words, I have given you a way of approximating this expectation, intractable expectation, by an empirical expectation, right? So that's why all this is connected. That this is where we started. This was our root cause of all the problems. That we had this intractable expectation and we wanted to do something about this. We still need to complete the full story, but we'll do that. First thing that we are going to do is we're going to look at these two expectations in their true form, that means in their exponential form, and then try to simplify it and then arrive at something which then we'll try to deal with the help of Gibbs sampling. Okay? So we'll look at some very simple maths. So you have to take my word for this, that this is what these two expectations were. We had actually rigorously derived them, and this is the function that we had inside the expectation. Okay? So I can write this as following. This is the true expectation. I sum over all possible values of h, and my expectation is over the distribution P of h given V, and this is the function that I care about, hi vj. Okay? And the second quantity is actually a sum over all possible values of V comma h under the distribution P of V comma h, and this is the function that I care about. Is that okay? Now let's just split this into two parts, right? So this is a summation over V and a summation over h, and this P of V comma h, I have just split it as P of V into P of h given V. Is that okay? I've just separated out the two summations. Everyone fine at this point? Please, okay. Now you see that this quantity actually repeats at both the cases, in both the terms. Okay? So let's look at that quantity and see if we can simplify it. So we'll just focus on this quantity. Fine? Now again, this sum is actually a sum over h1, h2, h3 up to hm. So I can split it into two sums. One is hi and the other is all the remaining his. Is that fine? Can you guys please show some more enthu? It's straightforward, right? I mean, or you are blank because you are surprised by what simple stuff I am teaching, or is it clear? Okay. So this is one of the h's and these are all the remaining h's. Hence this is bold and this is not bold. Okay. And okay, again remember that this conditional can be factorized, right? That's what our assumption was, that this was P of h1, h2, h3 given V, but we can just write it as P of h1 given V into all the other guys given V, right? That's the factorization that we have assumed in the case of RBMs. Everyone okay with that? Okay. So now I'll just take out the terms which are dependent on hi outside and I'll keep this inside. What is this summation? If you can answer this, I'll know that there's point in continuing this lecture, otherwise there's no point in continuing this. What is the summation? Everyone? Everyone? Right? The summation of all possible values that this guy can take, so that's going to be 1. Okay? Is that fine? Okay, so that means I'll continue with the lecture. Okay. And what is this actually? This summation has how many terms in our case? How many terms does this summation have? Which are the two terms? hi equal to 0 and hi equal to 1, right? So this actually is P of hi equal to 0 given V into hi vj and P of hi equal to 1 given V into hi vj. Which of these two terms will disappear? Hi equal to 0, right? Because you have a product of 0 here. So that will disappear. So this just boils down to P of hi equal to 1 given V into Vj. Is that okay? So notice that in the first term, which looked nasty, it had this big summation over all possible values of h. It turns out that this is actually not nasty, it just boils down to a very simple computation. So at least the first expectation, we have actually got rid of it straight away, right? We don't even need sampling to deal with it. It just boils down to a very simple term. What about the second expectation? That's again simplified, right? So it just becomes, okay, the first term is this. So now if I substitute this equal to this in this equation, I'll get the following. Okay, in particular note that from both the cases the summation over h has disappeared, right? But unfortunately in the second term the summation over v still remains. Okay, and this v is intractable. This summation is still intractable because it's still 2 raised to m. Okay, is it fine? Everyone okay with this? Right. So this is what we have come up with, and now can you give me a simple way of writing this term? What does this look like? If I assume that this is actually W, right? This matrix of all the weights is W, then can you tell me a simplified form for this? Oh, capital W into V. What is this? This is not a matrix product. This is a dot product, right? So what are the two vectors involved here? Wi and V, right? So this is Wi and V. So ith column of W and V. How many of you are fine with this? Please raise your hands. Good. So this is Wi and V, and the same simplification everywhere. Okay. Now this is the partial derivative of the loss function with respect to one parameter. Now can you give me the gradient of the loss function with respect to the entire weight matrix? Can you generalize from here? The hint is in this formula right now we have one column of the matrix. When we generalize, we'll have the entire matrix, right? If you get that intuition, the rest of it you can work out, right? So this is how the generalized form is going to look like. Okay. So starting with the same recipe that we compute the gradient with respect to one of the parameters, or rather the partial derivative with respect to one of the parameters, we now have a formula for the gradient, and this formula still has one problem, which is this. This is, how can I write this actually? If I denote this as f of v, how can I write this? What is this quantity actually? If I denote the sigmoid part as f of v, what is this? Expectation of f of v under p of v, right? And this is still intractable, hence we need to do sampling. Okay, fine. Is that fine? Okay. And that was wij. We can do the same computation for bj, that means the gradient with respect to bj, or the partial derivative with respect to one of the b's, and then we can generalize to the gradient. So you can go back and check this. Again, this will have this bad expectation term, and the same thing holds for the c's. Again, the c's will have this bad expectation term, right? So this math is very similar to the math that we did for wij. It's all straightforward. You can go back and check it. I'm not rushing because I don't have time. I anyways would have rushed through this, right? Okay. This is very straightforward based on all the stuff that we have done in this course before. This should be very trivial to understand. The key thing to note here is that all the three gradients that we have computed, that is the gradient with respect to W, the gradient with respect to B, and the gradient with respect to C, contains some expectation term. Okay, and this expectation with respect to the random variable V, which is a collection of all the visible variables, these expectations are intractable. So now to be able to do gradient descent, although we have a formula for the gradient, we need to do something. What will we do? We'll get rid of this intractable computation by doing Gibbs sampling. So we'll try to replace these expectations by their empirical estimates. And how will I get these k samples? By running the Markov chain long enough so that I start getting samples from the distribution that I care about. Once that happens, I'll take k such samples and substitute that here. And the reason I can do that is that because this chain is easy to set up, drawing samples from this chain is easy. So all these expectations I can replace by their empirical estimates by running Gibbs sampling. Everyone gets that? Okay. So now let's actually write the full RBM training algorithm. Pay attention, this is exactly what you're going to implement, okay, in the last assignment, which will be released over the weekend. So as input, you have this RBM, which has these visible and hidden variables, okay, and just assume that this is the training data given to you, all the training data that you have. The output is the learned parameters W, B, and C. You'll start by initializing the W, B's, and C's using whatever favorite initialization algorithm you have, not to zeros, not to equal values, not to large values. Now for all training examples belonging to your training data, what do you need to do? Okay, without me telling you the algorithm, okay, tell me what the last 3 steps of this algorithm are going to be. What are the last 3 steps of this algorithm going to be? W is equal to W minus eta into gradient, B is equal to B minus eta into gradient, and C is equal to C minus eta into gradient, right? So I need to first, the remaining steps are going to be about computing the gradient. For computing the gradient, I need to run Gibbs sampling. So the first block in this empty space is going to be about Gibbs sampling, okay? So I randomly initialize V0. This is the starting point of my Markov chain. So I've picked up some V0. Now I'm going to run the Markov chain for a large number of time steps, okay? Why have I split it as K and K plus 1 to R? I'm assuming that after K it is going to converge. Remember, the proof that we have done does not tell us when it will converge. It will only converge asymptotically, right? Only as n tends to infinity. In practice, the way you do it is that you run it for many time steps, and after say some 1 million time steps or 10k time steps or 100k time steps, you assume it has reached the stationary distribution, and from that point onwards, whatever samples you get, you assume it comes from your distribution, right? That's how you have to do it in practice. In practice, you cannot do the asymptotic stuff, which is up to infinity, okay? Fine. So that's how I have split it. Now, at every time step, what do I do in the Gibbs chain, in the Markov chain? I have started with V0. At every time step, what am I going to do? So remember that V0 is actually a collection of all my random variables. And in fact, I can also add the h's here, right? So h2 up to hn, and I have v1 up to vm, and I actually have the values for these. These are zeros or ones or whatever, right? Now, what do I do in my Markov chain? I need to pick one of these values, sample a new value for that. In practice, we do something very simple. We don't have this uniform distribution. What we do is that we go over these random variables one by one in order. We'll first pick up the random variable 1, change its value or retain its value based on the conditional distribution that we had defined earlier. Then pick up the random variable 2, change its value or keep its value depending on the random on the distribution that we had defined earlier. So what I'm saying is that our QI is very simple. It's just periodic. Pick up first, pick up second, pick up third, and so on. Just go over all the random variables one by one instead of sampling the value of 5, right? And the argument here or the rationale here is that anyways you are going to run it for many time steps. So anyways you are going to hit all of them once. So why not just go over them in order, right? That's the simplified thing. So you don't have QI in practice. You just go over all of them once. Now let's look at this even more carefully. And this is the difference between practice and theory, right? So the first difference is that we have gotten rid of QI. We're just going to go over the random variables one by one. Now ideally what would we have done, right? We would have taken V1, sampled a new value for V1 keeping everything constant, right? Then sampled a new value for V2 keeping everything constant. Then sampled a new value for V3 keeping everything constant. Do we need to do this one by one? When I'm sampling a new value for V2, do I need to wait for the step where I had sampled a new value for V1? The answer is no. Why? So I'm actually asking you the question V2 given all the other random variables. Okay, that means V1, V3 up to Vm and H1 to Hm. Now I don't care what these values are, right? Because anyways my VIs are independent of each other, right? So I can just sample V2 given the configuration of the H's. So even if my V1 had changed in the first time step, it does not matter because this probability is not going to change. How many of you get this? So what does that mean? Instead of changing one visible variable at a time, I can change all of them together, right? So I can do, so at every time step, instead of changing one of the visible variables, I can just change all of them together. So it's the same as running m steps of my Markov chain in one time step. I had m visible variables, I should have changed them one by one, right? It would have taken me m steps to go over all the visible variables, but that's just a waste of time because I don't need to wait for one visible variable to change to decide how the other visible variable is going to change, because the other visible variable does not depend on this visible variable. Is that clear? Right? That's why I can do this block Gibbs sampling. I can just change all the visible variables in one go, right? So that means that for every time step, I'm actually running m steps of the original Markov chain because I've done these m transitions in one go. How many of you get this perfectly? Please raise your hands, up and high. The ones who don't get this, I see a very less population of that, but what's the problem? Okay, so everyone gets this. So this is what block Gibbs sampling does. So remember that when I say one step, actually I've run the chain for m steps because I've done these m transitions, right, at one go. Fine. So what I'm going to do is first transition all the n hidden variables, okay, then transition all the m visible variables. So I said the order was go over all the visible variables and then go over all the hidden variables. What I have written here is just the opposite of that, but it doesn't matter, right? The order could be anything, right? So I just sample all the hidden variables, I sample all the visible variables, and I'm going to do this for a large number of time steps. That is a total of k plus r time steps, okay? So we have run the Gibbs chain. Now what am I going to do? At the end of this, I have some r samples which I believe have come from the distribution that I care about, right? Now the first thing that I want to do is, I want to compute this gradient. I want to do this update, okay? Why is there a minus, a plus instead of minus? We are maximizing the log likelihood, not minimizing it, right? So that's why it's a gradient ascent and not gradient descent, okay? Now I'm going to substitute this, okay? So this plus an expectation, and now I've replaced the expectation by this empirical expectation based on the R samples that I have drawn. Is that clear? How many of you are fine with this step? Please raise your hands up and high. Okay, good. And what's the next step going to be? B. Again it had that expectation. I'm going to replace that expectation by its empirical estimation. Again C had this expectation. I'm going to replace the expectation by its empirical estimate. Is that clear? Okay. So this is what you will implement for training RBMs. This gives you the entire algorithm. If you keep running this loop, so what I've done is here is, what am I running here? Stochastic gradient descent, mini batch gradient descent, batch gradient descent. Stochastic, batch, mini batch. Everyone? Right? I'm going over every example in the training data and the update is inside this loop. Right? So for every training instance, I'm making this update. Okay? And you also need to be clear about something. In this entire computation, which is this is my key computation, right? That's the computation which is updating the gradient. Where is the training instance being used here? I was just drawing some samples from the Gibbs chain, right? Where is the training instance being used here? Which is the training instance here? Remember, this first expectation was actually H given V. What was this given V? The training sample. That was the given V, right? So whatever V use here in the first term, which I've called VD, is actually a training instance. So the first expectation uses the training instances. The second expectation uses the sample instances. Is that clear? Okay? Everyone gets this? Okay. So that ends our discussion on training RBMs using Gibbs sampling. Now a very simple thing on training RBMs using contrastive divergence. So our question was that, again I'm anyways doing this n steps here, right? But the point is this n steps can be done together, right? So that's what the block Gibbs sampling is about. Okay? So just for clarity of notation that I've written it that way. Yes. So that is also done. You can reuse from wherever you had stopped. Right? So in practice that would be more meaningful Because that means, so it's a very valid question, right? So you're running this, no, wait, there's a problem there. At every point, you're drawing from this distribution. This distribution depends on the model parameters. The model parameters are changing at every training instance, right? So the distribution is changing, so you need to start it from fresh.
So new markup.
Yeah, new markup. Yeah.